Welcome back. We will start this day with two lectures by Matt Stoffregen from Michigan State University.
Yeah, great, thanks. The plan for today is to actually use what we did last time to prove a topological theorem, but we don't actually need any of the inside parts from the last talk. We can actually just take the output of that talk and work with it without necessarily remembering the construction. So maybe I could just say what we produced last time. The goal for somewhere through the second talk is hopefully we'll be able to prove this pretty cool theorem. But unfortunately that theorem's been around for a while, which is a bad sign. When you want to prove a theorem which has been around since the 90s, that means there hasn't been a lot of progress in the interim. Let's see what happens. So last time we constructed a map, SW, so just a map between two gigantic topological vector spaces. So this was some map that went between sections. Sorry, I should have said in the background that we have a four-manifold X, which is closed. And spin. So you have some closed spin four-manifold. And we constructed a map associated to it. So this is really SW depending on our choice of X and S. And it went from sections of one vector bundle to sections of some other large vector bundle on X. And we said that we wanted to, we wanted to somehow use the homotopy class of this map to have an invariant of the four-manifold X. But at first that seemed like a bad idea because both of these spaces, these are just vector spaces. So there's no notion of homotopy of maps between them, which is interesting. They're contractible. But we had a little bit more information. So we also knew that both of those spaces had actions by the group pin2. Where pin2, remember, is just the subset of the unit quaternions consisting of the unit circle together with the unit quaternion J. All right, so it's some slightly weird looking group. It's just weird enough that homotopy theorists don't know what it is because they usually only worry about the circle and cyclic groups. So it's just slightly weirder than the circle. But it was advertised last time that although the homotopy class of this map is not interesting, somehow this map has some additional special properties, and that homotopy among maps with those properties will be much more interesting. We'll have to start by just saying what the special properties of this map are, and then in the second half of the first talk we'll try to indicate why those special properties are useful. Great. Any questions though before we actually get started? Get started with it? Okay, let's just do it. Let's see what happens. So we have to write out the formula for SW, but just schematically. We don't really care too much about what the terms of the formula mean, although we made some effort to define them last time. So let's say what SW, this Heiberg-Witten map, applied to a spinner and a one form actually is. So it has three outputs. It's got a section of the first vector bundle, a section of the second, and the third. The first output was that you had the Dirac operator applied to your spinner. Now the Dirac operator is kind of like a derivative. And you also had the result of Clifford multiplication of your one form on your spinner. Right, so this is an element of the first vector bundle, or the sections of the first vector bundle. You also had a term I'm going to write in a slightly different way than last time, just to avoid having to write it all out again. You have some kind of derivative of your one form, but where you just take the positive part. And then you subtract off some term in the spinner, which we said was kind of quadratic. So if you remember from last time, this term, it had an expression like phi tensor phi dual in it. So it was something like this, but the exact form didn't matter. We can just say this is some term involving phi, which doesn't have any derivatives. It's just a bundle map, but it's not a linear map. It's not a linear map between bundles. And this is going to be a section of the bundle of self-dual two forms. So last time we wrote it in a slightly different bundle, but it's equivalent to this way of writing it. And then there was the last part of the operator, which is the gauge fixing condition, and this one lived in the last section of the bundle. So it just outputs a function. But the only thing that really matters about this is that the operator splits into two parts. So if you plug some stuff into it, you're really just evaluating some linear term, d. So SW is equal to d plus q, where d is just the Dirac operator on phi, which is like a derivative, this sort of exterior derivative term of A, and the d star operator on A. So all of those terms are linear, and this is some linear map. But the nonlinear part of the map is just, it doesn't involve any derivatives. So, we have to put on our analysis hat and say, like, okay, maps without derivatives are sort of, we'll just declare them to be trivial, If you're not differentiating anything, you're not even doing PDE, so what are you doing? This term, in some sense, is maybe less scary than the first one. All right, yeah. So we have this good decomposition. And yeah, in order to analyze this operator, maybe we first want to know a little bit more about the linear term. So now we get to continue with our analysis hat for a minute. So consider the linear part D. All right, so that's some map on sections. It takes smooth sections to smooth sections. But when you're doing analysis on a manifold, sometimes you want to consider like L2K sections instead of smooth ones. So that means we're going to complete this vector space with respect to some inner product to make it slightly bigger. So instead of considering actual smooth functions, or smooth sections, we'll consider sections which have like k derivatives in them for some large k. But the kth derivative doesn't have to be continuous anymore. We'll just say it's a reasonable L2 function. So we're going to tacitly replace this space. Maybe let's call this gamma 1 for the rest of the time, and this one gamma 2. We're going to replace those things with their L2K completions, which just means you're going to have things which aren't infinitely differentiable. They're only, pretty good differentiability. Oh, sorry. But we make an observation about this. If we want to, replace these spaces for whatever technical reason, then when we apply D to an element in the first space, right, we're actually taking a derivative. So the result is not going to be k times differentiable anymore. You're only going to have k minus 1 derivatives left, kind of. You've already thrown away a degree of differentiability. So this operator D doesn't actually take k times differentiable sections to k times differentiable sections. It sort of loses a little bit of honesty. And this is the sense in which we can say that Q is an easier term, right? If you haven't actually taken any derivatives in Q, so you don't lose any regularity, which is to say that Q actually defines a map from an L2K completion to the same completion. Yeah, how many people are actually like PD? Hopefully not too many people are PDE experts because you might catch any horrible mistakes. But okay, this is like elliptic PDE in a nutshell. So, all right, we've got our, D is called an elliptic operator. That's just a condition on some kind of linear operators, which will become significant in a moment. And what's good is that the nonlinear term of your PDE just is, it doesn't involve derivatives. But now we get to deploy what seems like a really overpowered theorem. So Q actually lands in this thing. Any k times differentiable function is actually k minus 1 times differentiable. So you get an inclusion like this. So the actual map on completions, D plus Q, is the sum of this one and this composite. But there's this great theorem. In this case, it's the relic theorem, which you could think of as a relic because you use it so much it seems very ancient. But it says that the embedding, this map from here into the second one, it's not compact, like this doesn't land in a compact set, but bounded sets here go to compact sets here. So this is maybe you could call it like a pre-compact map or something. It's usually just called a compact map, even though its image is not exactly compact, but bounded sets go to compact sets. And why that makes sense is that things converge in L2K if they converge with their kth derivatives. But yeah, somehow things that might be very far apart in L2K, so if their kth derivatives are far apart, they could still have all their first k minus 1 derivatives very close together. So the point is that this map actually, it really crushes things down a lot more than you expect, because things that are very far apart, when you keep track of their derivatives, like functions that oscillate very fast, they might be extremely close to this flat function in a lower norm, but if you keep track of their derivative, these two functions are very far apart. Sorry, and if you're a PDE person, you're probably deeply upset with me for one reason or another right now. But also, just as a matter of convenience, you can think of all of these spaces. I'll like say this multiple times. You might as well just think of them all as L2 functions on the circle. So they all pretty much look like that in practice. So you have to imagine whenever you were last in analysis, or whenever I was last in analysis, I don't know. But you should think of all these spaces as pretty much, they're basically functions on a circle. At least it's safe to imagine them that way. All right, anyway, so we're happy now. We've got our linear term, and we've got this term Q, which we'll call compact. And we also have some special properties of D. So D comes from an elliptic map, or from an elliptic operator, so it has the following property. D is something called Fredholm. So here when we say D, we mean its map on the completions. And now we're not going to think of the smooth versions anymore. When we say D, we usually mean the one on the completions. So D is Fredholm, which means that its kernel, just as a linear operator, and its co-kernel are both finite dimensional. Great. That doesn't seem that interesting. So normally, for an operator to be Fredholm, people define it on Banach spaces. In that case, you need one more condition, but this is okay here. And if you have a Fredholm operator, you can define its index. So the index of D is the dimension of the kernel minus the dimension of the co-kernel. Right, that actually makes sense. Normally, if you have some map between two infinite dimensional spaces, that expression wouldn't make sense. But here, that's all finite. So let's say we have gamma 1 and gamma 2. We're supposed to imagine a Fredholm operator as something that's interesting in a finite dimensional way and then boring in infinite dimensions. So like you have some chunk here, which we'll say is the kernel. And then you have some other chunk, which is the co-kernel. We can embed the co-kernel inside of the target because it's a Hilbert space. There's no funny splitting issues. And apart from those two pieces, this map splits into an isomorphism on complements of both sides. So you can choose a complement on both sides, and the map is just going to be an isomorphism together with those two pieces that aren't related. But the space of isomorphisms between two Hilbert spaces is actually contractible. So, basically there's the only thing interesting about this map, the only thing to remember is what its kernel and co-kernel are. But we can, maps like this have a lot of special properties. So one of them is that the index is constant in Fredholm families. So if dt is a family of Fredholm operators, parameterized by some real variable, then the index of d is constant. So the index of a Fredholm operator doesn't move in families. So that says these are kind of homotopically well behaved. And the other thing is that compact perturbations of Fredholm operators are still Fredholm. So if D is Fredholm, we could just call it Fred, but if D is Fred, then D plus C is Fred whenever C is compact. So a compact operator is just a linear operator that takes bounded sets to compact sets, or to pre-compact sets. So we already had an example of a compact operator here. Great, so in particular, D plus C is going to be connected to D just by the linear interpolation of them, and so they'll have the same Fredholm index as well. It might be useful, though, to note a generalization of this, which doesn't come up as often. So this is all very standard. It's in the back of, Donaldson's book, or Donaldson and Cronheimer, rather. But you can also do it all in a G equivariant way. So remember, all of our spaces here had G actions. And so you could just, use your inner theologian and remove the dimensions and just try to interpret weird expressions. So if all these spaces have G actions and D is G equivariant, well, it would be clever if we actually used a color for this. So if D is G equivariant, then kernel D and co-kernel D are not just vector spaces anymore. They're G representations. And then we could define the index of D to be a formal linear combination of G representations. So we'll define RG to be the ring made up of formal linear combinations of representations of G. So that's where you just take the free abelian group initially on G representations, and then you give it a tensor. You give it a ring structure by tensor product, or rather, that's how you get multiplication, and it inherits an addition under connected sum. So you define the sum of two representations by V plus W, and the tensor and the product is V times W. But also you have formal inverses. So it makes sense to talk about the co-kernel of D being subtracted from kernel of D. Right, so this RG is called the representation ring, and it's some cute object. And all these properties remain true even for G equivariant things. So if you have a family of G equivariant operators, you get a family index, and if you change it by a compact operator, the G equivariant index is unchanged. But it's kind of cool because you went from having a number, that's boring, but numbers are the same thing as elements of R of the trivial group. And now you have a family of G representations, where here G is going to be pinned to. All right. Well, what have I done with the, there it is. But yeah, so far what we have is all kind of standard. There's many different equations that you could have in gauge theory, and they all look like this. You get some Fredholm part, and you have some kind of non-compact term, which most of the time is going to be reasonable. But now we get a property which is special to the Seiberg-Witten equations, which also came up last time, which is that the preimage of a bounded set, so if you have this map and you take the preimage of a bounded set, it's still bounded. And that's not usually true. And we won't prove that, but that's the observation of Witten. And or rather that's the first observation, and it was generalized into this case by Furuta. Great. All right, so I think those are the properties that we want. In order to make this all into a convenient definition, though, let's say we have let's put it together. So a very Fredholm map F between two Hilbert spaces. So we'll say gamma 1 and let's call them H1 and H2 so we don't get confused. Let's say we have a map between two Hilbert spaces H1 and H2 where F is linear plus C, where C is some nonlinear operator. If, first of all, L is Fredholm, and it's linear. C sends bounded sets to bounded sets, and it's a compact. C sends bounded sets to pre-compact sets. Pre-compact just meaning they're quoted through as compact. And finally, the preimages are bounded sets. So bounded preimages are bounded. Or sorry, preimages of bounded sets are bounded. All right, so these are the kind of maps we'll be interested in. And now, we don't need anything anymore. It's abstracted out. Right, but what are these supposed to correspond to? So maybe let's just sketchily talk about G homotopy. So let's say G is a compact Lie group, or maybe, let's say G is a compact Lie group. We could consider if we have two spaces with G action, and x1 and x2 are G spaces. So these aren't four manifolds anymore, they're just G spaces. We could look at G equivariant maps between them. So we could have two G equivariant maps from x1 to x2 that are continuous. And then we could just define G homotopy in the completely natural way. We could just say f and G or f and little g are G homotopic. If there exists an extension, if there exists a big F from x1 cross I to x2, so where the G action on this thing is just G action on the first factor, such that F restricted to 0 is little f, and F restricted to 1 is little g. So it's just an equivariant map that has the appropriate restrictions on the ends. And so we can just define the notion of a G equivariant homotopy without worrying about it too much. It's not too terrible. And we can, instead of thinking of the category of topological spaces and the homotopy category of topological spaces, it's also totally reasonable to think about the category of G spaces and the category of G spaces up to homotopy. So, all the notions that we have for ordinary homotopy theory, you can ask similar but more annoying questions for a G homotopy theory, for any particular group G. Oh, maybe I didn't do a great job here, but hopefully that's okay. But any questions about stuff so far? Otherwise, we'll just keep pressing ahead with a couple definitions in this vein. Yeah, go for it.
Can I think of this L2K as just sublab spaces? Like, what's the difference?
Oh yeah, they're sublab spaces. Yeah,
okay.
Yeah. I'm trying not to. You're not supposed to have to know that. So yeah. This is like an analysis-free version of things. Right, but we need one notion from ordinary homotopy. We need one particular notion from ordinary homotopy, and its generalization to G homotopy. So let's say you're in the category of topological spaces. But actually, for everything today, it's more convenient to work with based spaces. So you have a suspension functor. Which takes any of you have your topological space X and you suspend it, which is the same thing as smashing with S1. So remember that the smash just takes your space X, you take the product with the circle, and then you mod out by anything that has a base point. So this is S1 times X, and you send to the base point anything that's the base point on S1 times all of X, union anything that's the base point on X times all of S1. So for example, S1 smash S1. Let's draw S1 as a line where you identify the two ends. And X is over here. If this is a base point on X, and this is well, let's say this is the base point on S1 and this is the base point on X, then this whole circle is identified to the base point, as is this circle, and this circle, and this circle. So S1 smash S1 is just a disk mod the boundary, for example. And more generally, S1 smash N is just Sn plus 1. So, you know, suspension just takes your spheres and moves them up a little bit. But we have a totally analogous notion for G spaces. So fix a G representation. V. The examples that will, the only examples that will be relevant to us are like, so some examples. We'll use what we call R tilde, which is a representation of Z2, where you have the origin and you just flip things across the origin. You know, the second favorite representation that we'll want to use is the complex representation of the circle, which just acts by rotation. And then there's one other representation that we'll talk about, which is H, the quaternions. And remember that the quaternions were a representation of pin 2, right? You can just use quaternion multiplication by elements of pin 2 to act on H. We'll also think about R tilde as a representation of pin 2 by just using the map from pin 2 to Z2. Anyway, for all of these things, you can define the one-point compactification, which we'll call V plus, or SV. And these are pointed spaces, where the point at infinity is the base point. So in the first example, the advantage of carpet is you don't break the chalk. That's pretty cool. Okay, the first example, R tilde plus, we have the origin down at the south, and then you have a base point at infinity, and the Z mod 2 action flips the two sides. That may be a terrible picture, but hopefully it's okay. Over here, the one-point compactification is the two-sphere. You have the north pole is the point at infinity, or is the base point, and the circle action just goes around the equator, and so on. H is not possible to draw from my point of view. But we can define suspension by a G representation by sending a G space X to SV smash X. And so you can check as an relatively easy exercise that the suspension of the sphere R tilde by R tilde is S 2 copies of R tilde. Or that it should be direct sum, rather. Great. But this actually sort of, it's just furthering the analogy that was on the board before. Whenever you saw a number in ordinary homotopy theory, what you were actually seeing was a representation of the trivial group. And if you want to generalize things to G homotopy theory, whenever you saw a number, like in a homology group, like Hn as a homology group, or pi n, the nth homotopy group, you should make that number be a representation of G. So instead of having the nth homotopy group, in G equivariant homotopy, we have the vth homotopy group, which is the match from the sphere SV instead of the ordinary sphere. Which sounds more exciting than it is, maybe. All right, and finally, we want to pass to stable maps instead of just ordinary maps. A stable map in a non-equivariant context, a stable map between spaces x1 and x2 is just a map that doesn't show up for a while. You get a map after you've suspended a bunch of times. So a stable map is just a map that occurs on some suspension. And a stable homotopy between stable maps is just, well, you may not have a homotopy at this time, but if you have your two maps and you stabilize them some more, a stable homotopy is just a homotopy between them that eventually shows up. So stable homotopies will define an equivalence relation on stable maps. And we'll let x1, x2 be the set of maps between these two up to stable homotopy of maps. stable maps from unstable homotopy. And we can do the same thing in the G equivariant case, which I won't write down, which is just a stable map of G spaces is a map that doesn't show up until after you've done a bunch of suspensions by G representations. And then you also can define G equivariant stable homotopies the same way. Yeah, that seems relatively reasonable, right? And if you wanted, one could be more careful about it, and you can actually define a category of spectra on both sides where you've formally inverted the suspension operator to some extent. So in the first case, there is a way to formally invert it. It's just totally formal. And in the second way, I gather the homotopy theorists desperately want to do it formally. But there's an explicit but not abstract nonsense way to do it in the G case. All right, cool. What was the point of all that? Well, we wanted a home for this kind of map that didn't involve infinite dimensional nonsense. So now we can state the theorem, which actually already appeared last time, but yeah, this being slightly wet is good because then I have to ask for questions while we wait like a few seconds for it to dry. So yeah, what's new? Any questions at this point? All right, cool. So the theorem. I should also specify that a very Fredholm homotopy is just a homotopy through very Fredholm maps. Okay. So theorem, very Fredholm maps H1 to H2, where these are both G representations, modulo very Fredholm homotopy. Are in one-to-one correspondence with stable maps. So equivariant stable maps in S index of L to S0 mod stable homotopy. Well, yeah, I mean, I guess this group is already mod stable homotopy. So yeah, the maps between, very Fredholm maps between these two vector spaces were actually just determined by, this homotopy group. So I should have said sub G. That means to consider the space of G equivariant stable homotopy classes instead of just ordinary ones. And remember that index of L was supposed to be some kind of representation. So at first, right, this looks a little bit surprising because you might say there's not really any maps from a big sphere to a zero-dimensional sphere. But remember that these are only stable maps, so they don't have to show up immediately. You could have to suspend a bunch of times before you actually see the map. All right, and this is effectively from the 60s due to Schwartz, and it was sort of redone by Furuta, and I don't know. It hadn't really appeared precisely. But yeah, in the next part, we'll try to sketch in extremely sketchy fashion a proof of that result. And then put it to work. Okay, so one direction isn't really very interesting. Going from having a map, you can just sort of thicken it up to get a map between Hilbert spaces. So what we want to do is provide an extremely sketchy justification for why you can go from a map between two big vector spaces and turn it into a finite dimensional map. And as usual, we'll start off with kind of a really disappointing schematic picture. Okay, we got H1 and H2. Right. And right, you're supposed to think of both H1 and H2 as being L2 spaces on the circle. So they're supposed to just be, L2 of the circle. But L2 of the circle has a nice basis in terms of the Fourier, functions. So you can imagine that this is pretty much the span of the functions on the circle, e to the kix, where k is going from, okay, k is a really poor choice of letter, but e to the mix, where m is in z. So x is just a variable on the circle, and you have all these basis elements for your Hilbert space, kind of. And when you think of this as L2k, so if H1 is sort of L2k of this, rather, the L2k norm of e to the mix is just measuring the kth derivative. But the kth derivative of e to the mix is just going to be m to the kth times the size of e to the ix, or e to the mix. So taking derivatives has the effect of rescaling the norm, and it sort of breaks up the different eigenstates according to their energy. So you have maybe, let's call this direction E1, and maybe E1 is E1 differentiated is just E1 again, but E2 and so on. We're supposed to imagine the map from H1 to H2 as like a derivative. So it tends to take E2 and send it to pretty much the same function, but it's twice as long. And similarly, the third basis element is going to get stretched out even further. Whereas our map Q, right, if we take a bounded set, let's just take some bounded set B to start with. Our map Q sends it forward to a pre-compact set. And rather, in this picture, where both of these we're using the L2 norm on both sides, it just sends it to some bounded set. But the point is, as you get out to higher and higher energy terms, right, the linear part D, or in that notation, L, is sending these vectors really far out. Like if you plug in a really high energy Fourier piece, it gets sent way further than Q is going to go on that piece. So the idea is that for the most part, the map Q doesn't matter. Q might be stronger than L, but it's only ever going to be stronger than the linear part L on low energy pieces. And as you get further and further out into these the higher parts of your Hilbert space, then Q is just going to be kind of sad. It won't have a lot of energy, but L is going to be sending things flying all over the place. So the rough sketch is that in high energy parts, L is completely overwhelming Q, and the map looks linear. So with that being said, what we can hope to do is we'll just take finite dimensional pieces and look at the map on those finite dimensional pieces with the idea that eventually the map outside of those pieces will be linear. So we're going to pick V in H2. It didn't break too much, actually, but we're going to pick V in H2 and let L inverse of V be U. So you have some subspace up here, which is going to be. All right. And now that we have those two finite dimensional pieces, we want to ask, can we get a map between them that would make sense as a homotopy class over here? All right, so we could try to just apply our very Fredholm map F from U to V, but that's not going to land at V. So instead we'll use an approximation. A is going to be equal to the linear map L, which takes U to V, and then we'll just project back into V. So you take the nonlinear part C and you project it. And the point of this is that approximation A is actually really close to the original map that you had, exactly because C, at least in the high energy part, is not that interesting. So pi V applied to C, if V is large enough, is very honest. And the property 3 over there implies that A is proper. And once you have a proper map between two vector spaces, so meaning the preimage of compact sets is compact, then you'll observe that if we took a ball in U, let's say this is the ball of radius 1 in U, and we mod out by the boundary, maybe 1 is a placeholder, you might have to use a higher radius. By properness, if we go far enough out and modding out by the boundary, then this stuff cannot go to 0. So it has to go far away from the origin by properness. So we can say this goes to the ball in V of radius epsilon, mod out by the boundary of the ball, V, radius epsilon. Because anything far enough away from the origin in U cannot get too close to the origin here, so that this map makes sense. Once you mod out by the boundary of a ball, you get a sphere. So this is SU, and this is the unit sphere. Sorry, this is not the unit sphere, but this is a sphere which we'll call SU, and this is a sphere which we'll call SV. All right, great. So we got a map between two spheres, but now we have to look at what are V and U. What are the relationship between V and U? Well, V is the preimage under L of U, and if you think about it for a little bit, you can use the definition of the index to see that the index of L plus U is equal to L inverse of V in the representation ring of V. Sorry, this is V itself. I meant to say L inverse of U, or sorry. This should be V, and this should be U. But yeah, I mean, the index measures how much of a difference in dimension there is between those things. So this is, this is the Fredholm index at work. It measures what kind of finite dimensional map you have. Great, so you have a map between two spheres, and even better, you know the difference in their dimensions. This is actually V plus into L. So you've just found a map in S into L to S0. I mean, it doesn't feel like you found a zero sphere anyway, but anywhere here, but you did in effect. And the point of that discussion about the energies earlier is that if you start increasing the size of the representation V over here, then the preimage over here increases, but it only increases in high energy directions. And Q on the high energy directions just doesn't do anything. So you get effectively the same map you had before, plus an isomorphism in the new directions, which means as you make this approximation bigger, you have just one map, and then you stabilize it effectively by the identity as you get bigger and bigger spheres. All right, so that was a pretty terrible sketch of going from having a very Fredholm map to getting a stable map out of it. But yeah, even if it's not very precise, it seems kind of fun. And I should say that even though this argument is totally non-specific, or not precise, it's actually pretty close to what you do. I mean, in terms of fake sketches, it's reasonably honest. So let me just summarize what happened then. And then we'll execute the final step of this, evil plan at the beginning of the next one. So we started off with our four-manifold XS. And then last time we alleged that you could turn it into SWXS, which was a map as above. It was some giant map between Hilbert spaces, but it actually turned out to be a very Fredholm map. So from the four-dimensional topology, you get a very Fredholm map. And mentally, not only, you could call these very Fred, but you can make it even worse. Whenever I see it, I just think it's very Freddy. But it's, yeah. Anyway, you get a very Fredholm map, and we've just seen that you have this other fun theorem that converts that into an equivariant stable homotopy class. So an element, and this called the Bauer-Fruta invariant of XS, which lives in G equivariant maps. So it actually lives in the index L equivariant homotopy group of the zero sphere. And we say it's in the index L homotopy group because we're looking for maps of spheres from the index L sphere into S0. Maybe in the last 20 seconds or something, I want to specify one more thing about this. which is that the index of L, this just comes from the linear part, and in principle it's very hard to calculate. But there is technology to calculate it. Namely, the Atiyah-Singer index theorem has a topological machine for you to calculate the indices. And we won't state the Atiyah-Singer index theorem, but we will need the output of it. So let's just say that Atiyah-Singer says that the index of L, for the particular L that we're using here, is minus the signature of your Floer manifold. So our Floer manifold was X. Yeah, that's kind of designed to make a talk stop, isn't it? Is times the quaternion representation minus B plus R tilde. So it's the size of the maximum positive definite subspace of your, the intersection form of your Floer manifold times that representation R tilde we had before, and then you also get some copies of the quaternion representation. So actually it lives in a pretty reasonably specific homotopy group. And this is an invariant of the smooth structure of your Floer manifold. So one is very happy initially. Like, it's hard to get invariance of the smooth structure of your Floer manifold. And we'll see that that invariant can do something in the next talk, and then we'll see that we actually don't really know anything about it. But that looks like a good place to stop. So thanks.
Questions? Okay, so let's thank Matt again. Let's start the recording.